Imagine an airplane is flying overhead at a constant elevation of 4,000 feet. There's a man standing 3,000 feet away from the radio tower, just standing on the ground. The plane is going to fly over the man. We want to know at what rate is the distance between the man and the plane increasing, specifically when the plane passes over the radio tower. First thing that I recommend doing is draw a diagram that helps you understand the setup for this problem. So I have a plane that's 4,000 feet above the ground. I have a man that's standing 3,000 feet away from a radio tower, and I want to imagine that plane flying over the top of the head of the man towards the radio tower. And then I see that some things are changing as that plane gets closer and closer to the radio tower. The distance between the man and the plane could be represented diagonally or horizontally. I've drawn right triangles at 3 different snapshots in time. I'm going to separate those to make my little diagram. So at some point the plane just passed over the man. We have a right triangle to represent that. As time goes on, the plane gets further away, so I have a different triangle. And then at the very last snapshot in time, I've drawn a picture where the plane is perfectly above the radio tower. Now I want to highlight the quantities that are changing in these 3 different stages of the diagram. I can see that the horizontal distance between the man and the airplane is changing. So that's a quantity that's changing over time. But also the diagonal distance between the man and the airplane is changing. So there's another quantity that's changing over time. We're asked to specifically find the rate of change for the distance between the man and the plane when the plane is above the radio tower. Now we have 2 distances that are between the man and the plane. One of them's horizontal, one of them's diagonal. Because the problem doesn't specify to measure the rate of change for the horizontal distance, we should assume it's the direct distance. That's that diagonal. But both of these quantities are changing, so they both need symbols. We'll use x to represent the horizontal distance. It's changing with time, so x is a function of t. We'll use s to represent the diagonal distance, also changing with time, so s is a function of t. Since both of those quantities are changing, they both will have rate of change. So the derivative of x, dx dt, will be the rate of change for the horizontal distance. And then ds dt will be the rate of change for the diagonal distance. That wraps up step 1. We've drawn a figure, and we've identified 2 changing quantities and assigned symbols for the quantities that change, as well as the rates of change for those quantities. We can move on to step 2, which is to identify the given information in the problem and identify what's being asked of us. We can see that they tell us that the plane is flying at a rate of 600 feet per second. The plane is flying at a constant elevation of 4,000 feet, which means it's flying perfectly parallel to the ground. That means that the horizontal distance is changing at the same rate as the plane is flying. So we can use the speed, 600 feet per second, and say that that is the same as the rate of change for the horizontal distance, which is dx dt. We're asked to calculate the rate of change for the distance between the man and the plane. That would be that diagonal distance, ds dt. We're trying to calculate ds dt specifically when the plane is above the radio tower. And if we look at the things that are changing, the best way to represent the moment in time where the plane is above the radio tower is to say that the horizontal distance between the man and the plane is 3,000 feet. It's gone all the way over the distance between the man and the radio tower. Now that we've done that, we're ready to move on to step 3. In step 3, we need to come up with an equation that relates the 2 quantities that are changing. So we need one equation that relates x, the horizontal distance, to s, the diagonal distance. And because we have 3 right triangles, we should try the Pythagorean theorem. That's not always the answer, but we should try it. So if I drew a right triangle for this first moment in time, I could use the Pythagorean theorem to relate x and s. I'll try it again for the second snapshot and the third. And I can see that everything's pretty much the same from snapshot 1 to 2 to 3. The only difference is I would have to update what the horizontal and diagonal distance is in my equation. So instead of saying x1 squared or x2 squared or x3 squared in each one of these scenarios, I can simplify it and just say x, which is changing with time. Same thing with the diagonal distance. I can use s because that changes with time. So we've got an equation that says x squared plus 4,000 squared is equal to s squared, where both x and s change with time. We can take that equation, which relates our two changing quantities, and apply implicit differentiation. Remember, x and s both change with time, so we'll differentiate that entire equation with respect to t. Applying implicit differentiation, we get the related rates equation. Here we have 2x times dx dt is equal to 2s times ds dt. We're ready to plug in our given information, but we should first reduce any known easy reducible factors. So there's a factor of 2 on both sides of the equation, so we can divide that off. We are told to find ds dt knowing that dx dt is 600 feet per second and x at this moment in time would be 3,000. But we have a bit of a problem. There is a value that we don't know. We need to know what s would be at this moment in time. S is that diagonal distance. So when x is 3,000 feet, can we find the diagonal distance, s? We can. In fact, we can just draw that right triangle from the last snapshot in time. We know that the horizontal distance is 3,000 feet when the airplane is above the radio tower. We know the airplane is always 4,000 feet above the ground. We just need to find the diagonal distance at this snapshot in time. This happens to be a 3, 4, 5 triangle. And if you're not familiar with that, it's a special triangle that can scale up or scale down. So the ratio of 3, 4, 5 is what we're looking at, and we've just scaled it up by a multiple of 1,000. So we have a 3,000, 4,000, 5,000 triangle instead of a 3, 4, 5. Great, we have s now. We can plug that into our equation and solve for ds dt. So we'll have 3,000 feet times 600 feet per second. That will be equal to 5,000 feet times ds dt. We can divide the entire equation by 1,000 to reduce some of our factors, and then we're left with 3 times 600 on the left-hand side, and that would give us feet squared per second. On the right-hand side, we have 5 feet. If we divide both sides by that 5 feet, we're left with 360 feet per second. So the rate of change for this diagonal distance when the plane passes over the radio tower is 360 feet per second.